We were able to fly from Earth to the moon because Newton knew a lot about gravity. Sometimes you might get lost in the passing of time and wonder if what we know about it is just the tip of the iceberg. His new discovery is not just an idea. It's a key that could open the doors to the mysteries of the universe and show us a world that is more complex and amazing than we ever thought possible. In what ways does Brian Cox's new theory challenge the way we usually think about time? What might this mean for how we see the world? Come with us on an interesting journey through the history of time as we look into Brian Cox's new, groundbreaking idea about how time works in the very large universe we live in. There are puzzles out there to be solved. Some of these mysteries have to do with time and gravity, which are very important to our lives. One possible world is one in which time moves in a strange way, either slowly or quickly. Also, the force that holds us down might not be what it seems to be. In this area of Albert Einstein's theories of relativity, our ideas about time and gravity change in a strange way. His theories of relativity gave us a new way to think about the world. Albert Einstein is a famous person. His work made it possible to learn about how time changes in different settings, especially when moving very quickly. Einstein came up with two theories that changed the world: the special theory of relativity and the general theory of relativity. This was the start of it all. When it came out in 1905, the special theory of relativity changed the way we think about time and space. This basically means that the rules of physics don't change for people who aren't speeding up, no matter what they're doing. In this theory, relativistic effects are first mentioned. One well-known effect is that time can stretch out or slow down in some situations. The light clock is an interesting thought experiment that is used to show how time slows down. Imagine being in a spaceship that is going very, very fast, almost as fast as light. There is a beam of light bouncing between two mirrors inside the rocket that is not moving in the same direction. The rules of physics say that the speed of light stays the same for all observers. This means that the light beam must look like it is moving diagonally. Here's the interesting part. Both people inside and outside the spaceship should see the same amount of time pass as the light beam moves along its path. From the outside, though, the road looks longer, so it seems like it would take longer for the light to make its trip. Einstein called this difference in what seems like time between the two viewers time dilation. For the observer who is moving, time moves more slowly than for the spectator who is still. In this case, time acts differently based on how fast you're moving. It is not just a theory that we should understand relativistic effects, which are the ways that things change when they move quickly. Large Hadron Collider and other particle accelerators are used by scientists to make particles move very quickly, almost as fast as light. Things move so quickly that we need to change the way we think about time to be able to forecast and measure things correctly. In 1905, Albert Einstein came up with the special theory of relativity. This theory changed the way we think about the world, especially when it comes to time and how things move. This idea goes against what we might normally believe. The rules of physics are the same for everyone, even if they're not moving. In everyday life, we might think that adding speed to something that is already moving makes it go faster. On the other hand, Einstein's theory says that the speed of light is the fastest thing that can move. Think about it this way. Things that happen at the same time to us might not seem that way to people who are going almost as fast as light. Length reduction is another thing that happens when you look at things in this way. This means that if you look at something that isn't moving, it looks shorter in the direction it's going. You can also think of the famous equation, energy equals mass times the speed of light squared. It comes from this way of thinking. This is a very important discovery because it means that energy and mass can change into each other. This helps us understand how tiny particles behave when they're moving very quickly, and also what happens when atoms split in nuclear reactions. Special relativity isn't just a fancy theory in the real world. We use it in regular technologies like GPS. There is motion in the GPS satellites when they send messages to your device. This makes time behave differently for them. Your GPS tracking would be very wrong if we didn't take this time dilation effect into account. We learn from special relativity that time isn't the same everywhere and for everything. Things are going in different ways. This idea makes us think about time and place in a new way. Saying that our normal view of the world is a little off is the same thing. The special theory of relativity says that motion changes time, so it's not set. A lot of tests have shown that some basic ideas are true, like how the speed of light stays the same and how energy and mass are linked. But there's more. Here comes Einstein's general theory of relativity, which he wrote in 1915. This idea goes into a lot of detail about how gravity works and how the world is put together. That gravity is just a force that pulls things from far away is no longer true. Gravity is caused by space and time being twisted, not the other way around. That's like saying, hey, gravity isn't some strange force. It's just how things move in the universe. According to Brian, to understand general relativity, you have to think of the world as having 4 dimensions, 3 of space and 1 of time. Things that are big, like stars, planets, and even us, change the shape of space and time around them. This is what we think of as gravity. Think of space-time as a big blanket that you can stretch out. Putting something heavy on top of it, like Earth, makes a hole in the cover. It will roll toward this din if you put something small, like a ball, close to Earth. This is like how things move because of gravity, which is not some mysterious power but a response to the way space-time is warping. It's like the Earth makes a small dip in the fabric of space-time, and everything moves around that dip. The theory of general relativity gives a good account for how things move in our solar system, like how the planets move around the sun. It can correctly show the paths these planets take, like how Earth goes around the sun in an oval shape. Brian says that this is not the same as the old idea that gravity just pulls things together, which didn't help explain how planets move. The new idea is that time and space are curved like a stretchy material. This thought matches what we see better. An eclipse of the sun in 1919 was a big event that proved general relativity to be true. A group led by Sir Arthur Eddington looked at how light from faraway stars bent as it came close to the sun. The idea says that because the sun is so heavy, the starlight would curve a bit. During the eclipse, the observations exactly met Einstein's predictions, which proved that the theory was correct. To put it simply, special relativity says that gravity changes time in the same way that motion changes it. Time moves more slowly in places where gravity is strong than in places where gravity is weak. That is, if you were close to something very big, like a black hole, your clock would move more slowly than if you were far away from it. In general relativity, the idea of black holes is introduced. Black holes are places where gravity is very strong. There is such strong gravity inside a black hole that nothing, not even light, can get out. People say that the event horizon is the edge of a black hole. It's like a point where you can't go back. If something goes past this line, it will be pulled into the black hole and never come back. The way the world is put together is changed by Einstein's theory of general relativity. He first added something to his equations that he called a cosmological constant because he thought the world wasn't changing. He said this was a big mistake when we found out it was growing. A key part of the Big Bang Theory, which explains how the universe started, is the idea that the universe is getting bigger. This idea comes from general relativity. Gravitational waves are another important idea from the theory of general relativity. These look like waves in space and time that are made when very heavy things move very quickly, like when black holes or neutron stars collide. The Laser Interferometer Gravitational Wave Observatory, LIGO, directly observed gravitational waves in 2015, which proved another part of Einstein's theory. Scientists have done many tests over the years to see if general relativity is true, and each time it has been found to be correct. There has always been evidence to support the idea, whether it's looking at how planets move, how starlight bends, or how gravitational waves are picked up. It might seem strange to say that gravity is a lie, since we all feel it every day. But in the field of physics, it's normal to talk about and look into different ideas. Scientists like Brian often question ideas that everyone else agrees on. When it comes to gravity, some people question how we usually think about this basic force. Modified Newtonian dynamics, MOND, is an idea that goes against the idea of traditional gravity. It says that gravity works differently at slow speeds, especially in galaxies, and it doesn't need dark matter to do this. MOND says that gravity gets stronger at low speeds instead of adding matter that can't be seen. In the discussion about gravity, there is also the mysterious dark matter and dark energy, which were created to explain some things that happen in space. Some people say that these aren't needed because other ideas can explain what we see. There are experts who don't agree with Einstein's theory of gravity, look into new ideas that might change or add to what we know about gravity, like theories about unknown objects or forces. To be clear, new ideas are not thrown out in science. Instead, they are carefully examined to see if they make sense. Einstein's idea about time in four-dimensional space, where the speed of light might make it impossible to go back in time, has been thought about artistically along with wormholes and shortcuts. Stephen Hawking's chronology protection hypothesis says that from a physics point of view, going back in time doesn't seem likely. Experiments and observations are still going on to see if these new ideas can explain things like gravity in a way that is close to what we already know. Many ideas have been put forward, but none of them have been able to successfully replace the well-known rules of gravity. Scientists learn new things by having doubts and not agreeing with ideas. This leads to more study and a better understanding of the universe. When it comes to gravity theories, general relativity is still the best and most important one. Even though there are problems and other ideas, it always does well in tests and explains things like how planets move and how light bends around big things. General relativity is still strong because it's easy to understand and applies to many different types of events. Like we said before, Einstein's special theory of relativity says that time can change depending on how you're moving. Let's look at how this idea works in the real world, especially when it comes to space travel. Einstein's theory says that the speed of light is the fastest thing that can go in space. This makes spaceflight both exciting and difficult. Because of this, moving between stars is very hard, even with very advanced technology, because it takes a long time to get to the nearest stars. Think about the well-known twin paradox to get a sense of what happens to time when you go into space. Imagine that one twin stays on Earth while the other twin travels to a faraway star. They find that less time has passed for them than for their twin on Earth when the twin who went into space comes back. In a way, this means they go to the future. They need to keep track of time because time slows down more as the trip goes on. People might age more slowly than people on Earth if they go to close stars where time moves much more slowly. It sounds like something out of a science fiction story, but it's a real result of the theory of relativity. What if people sent a group of people to a nearby star system? The trip could last for many years because it's so far away. The people on the spaceship would feel like time is moving more slowly, even if they go fast. On Earth, however, a lot of time would have passed. Not only does time dilation affect live things, it also changes technology. For accuracy and proper operation, computers and communication tools on spaceships need to take time dilation into account. When traveling through space at high speeds, there are physical problems, like being alone for a long time and being exposed to cosmic radiation, as well as mental problems that come from being away from Earth for a long time. The Global Positioning System, GPS, lets us see how time has slowed down in our daily lives. GPS depends on information from moving satellites arriving at the right time. Because these satellites experience time dilation, it's important to take these effects into account when doing GPS estimates. Not doing this would have a big effect on how accurate navigation devices work. Let's look into why time goes in one way. The world is run by time, which flows from the past to the present to the future. Time moves only in one direction, which is an important part of our lives. But why does time move only in one direction? To help you understand, let's look at entropy, an idea that measures how chaotic or random a system is. The arrow of time is linked to entropy, which tends to rise over time. This makes time flow in one way. This connection is shown by the second rule of thermodynamics, which says that total entropy will either rise or, at best, stay the same in any closed system. Without going into too much detail, entropy tends to rise and not fall. Seeing how things get messy around us helps us understand that time moves in only one direction. Picture a deck of cards that are all in order. They become messy and random when we mix them up. From order to chaos, time moves in one way, as seen in everyday things like ice melting or a stirred coffee cup getting messy. At different stages, this flow of time works in different ways.